Yeah, good evening all. Now we will discuss about center tapped rectifier. Okay, here it is the schematic arrangement of a center tapped rectifier. Okay, this center tapped rectifier consisting of a step down transformer. Okay, here it is a center tapped transformer. The center tapped transformer means the tappings will be provided from the center of the transformer, right? See here, this is one conductor, this is another, and this is another one. That means it is having three leads, three wires. That means here 6 volts, this is my assumption, 0 volts and 6 volts. Okay, phase neutral, again phase neutral. Okay, in this way voltage will be divided in case of center tapped transformer. Okay, this rectifier consisting of a center tapped transformer and two diodes, diode D1 and D2, and a load resistance RL is connected between the center of the tapping of the transformer and cathode of the two diodes. Okay, here output voltage will be measured across the load resistance RL. Okay, this is the construction of a center tapped rectifier. Okay, now we will discuss about the operation. Okay, already we know that AC is having positive half cycle as well as negative half cycle, right? Now based upon those two half cycles, the operation will be divided into two modes, operation 1 and operation 2. Okay, now see here in operation 1, that means during positive half cycle. Okay, during positive half cycle, plus comes here and minus comes here, plus comes here and minus comes here. See here, plus is given to anode and minus is given to cathode of the diode D1. Then diode D1 is in forward bias. When diode D1 is in forward bias, it acts as a closed switch. Closed switch means it acts as a short circuit, right? Similarly, okay, when minus is given to D2 anode and plus is given to D2 cathode, diode D2 is in reverse bias. When diode D2 is in reverse bias, it acts as a open switch. No current is flowing through the load, right? Then see here, that means during positive half cycle, D1 will conduct, D2 will not conduct, right? Then output voltage, this is the direction of current, right? Then output voltage V0, okay, based upon this current direction across the polarities will be plus minus, right? This is the output voltage. V0 is the output voltage across the diode. Okay, then output voltage will be again same as input voltage during positive half cycle. Okay, that is, you can observe here from the waveform. Okay, this is positive half cycle, right? Okay, during positive half cycle, diode D1 is in forward bias, D2 is in reverse bias, but the output voltage will be same as input voltage. Here Vs is present, here Vs is present, right? Then V0 is equals to Vs, right, to satisfy KVL in above loop. That means output voltage will be same as input voltage. Output current is also in phase with the output voltage, but magnitude is less, right? Okay, that is about in case of positive half cycle. Next, during negative half cycle, minus comes here, plus comes here, and minus comes here and plus comes here, right? That means plus is given to D2 anode, minus is given to D2 cathode. Then diode D2 is in forward bias, right? When diode D2 is in forward bias, it acts as a closed switch. That means it acts as a short circuit, right? When minus is given to D1 anode and plus is given to D1 cathode, diode D1 is in reverse bias. It acts as a open switch. No current is flowing through the diode. Okay, based upon these supply terminals, here supply terminals are reversed, right? This is the direction of current, higher potential to lower potential, right? Based upon this current direction, polarities across the load resistance will be plus minus. Here it is the V0, right? Now see here, in case of during positive half cycle also, the voltage polarities will be plus to minus. During negative half cycle also, the polarities of the voltage will be plus to minus, right? The current direction is not changed, right? That means in operation 2 also, the output voltage you will get only in positive half cycle. If supply terminals change also, output voltage direction or output current direction is not changed, then you will get output voltage in positive half cycle only. Okay, that means during negative half cycle, D1 is in reverse bias and D2 is in forward bias, right? The reverse bias diode acts as a open switch, that means open circuit, and forward bias diode acts as a closed switch. That means it acts as a short circuit. Okay, See here, we are changing the supply terminals, but the current flowing through the load direction is same, that is in case of same as positive half cycle direction. Hence output voltage is also present only in positive half cycle only. Okay, that is the variation here. Similarly, D1 will conduct here, D2 will conduct. Okay, in this way you will get output voltage for a full wave rectifier. Now we can observe here, in case of full wave rectifier, output voltage will be present in both half cycles, positive cycle as well as negative half cycle, right? Hence the name of the rectifier will be full wave rectifier. Why? Because you will get output voltage in both half wave as well as full wave, sorry, both positive half cycle and negative half cycle. Okay, that is about the operation of a center tapped rectifier, right? Next we will see the specifications like average value, RMS value, form factor, peak factor, right? First, average value, right? Average value, V average is equals to, see here the repeated waveform will be every pi seconds waveform will be repeated, right? Then time period will be pi, that is 1 by pi integration 0 to pi Vm sin omega t d omega t. Then V average is equals to, I can take Vm as common, you will get Vm by pi integration of sine, you will get minus cos omega t. Limits will be 0 and pi, substitute upper limit, after that substitute lower limit, right? You will get Vm by pi okay. V average value is equals to Vm by pi, upper limit will be pi, right? That is minus cos pi, minus of minus, you will get plus cos 0, you will get V average value will be 2 Vm by pi. Similarly, RMS value, V RMS is equals to under root 1 by pi integration 0 to pi Vm sin omega t whole square into d omega t, that is under root, can take Vm square as outside, then Vm square by pi integration 0 to pi sin square omega t d omega t. That means Vm square by pi sin square omega t can be written as 1 minus cos 2 omega t by 2 into d omega t, right? If I take 2 as outside, you will get under root Vm square by 2 pi integration of 1, you will get omega t, cos 2 omega t will be sin 2 omega t by 2, substitute upper limit as pi and lower limit as 0, right? Then you will get Vm square under root Vm square by 2 pi, upper limit will be pi minus sin 2 pi value will be 0 minus 0 minus of minus plus sin 2 into 0 by 2, that is sin 0. You will get, after simplification, VRMS value will be Vm by root 2. Okay, next form factor, already we know that RMS value divided by average value. Okay, then form factor is equals to 1.11. okay, similarly peak factor is equals to maximum value divided by RMS value, that is Vm by root 2. Then peak factor value will be 1.414. okay, next peak inverse voltage will be minus 2 Vm. okay, this is the important point here. Now you can observe here, either it is in positive half cycle or it in negative half cycle. See here, in any operation, when one diode is in forward bias, one should be in reverse bias, right? Now see here Vs voltage is present, voltage across the load resistance is also Vs, output voltage will be same as input voltage, right? Okay, that means during positive half cycle D1 acts as a closed switch, that means it acts as a short circuit, D2 acts as a open circuit, right? If I apply KVL here, see here minus plus Vs minus Vs minus plus minus Vs plus voltage across the diode is equals to 0, then voltage across the diode will be 2 Vs. That means in this case, this diode must and should bear 2 times of supply voltage. That means if we consider maximum value, it must and should bear minus 2 Vm. okay, that is the major drawback of this center tapped rectifier. Peak inverse voltage will be minus 2 Vm. That means that diode must and should bear 2 times of maximum voltage. okay, that means we need to manufacture the diode, that diode must and should bear 2 times of the supply voltage. okay, that is the major drawback of the center tapped rectifier. PIV is equals to minus 2 Vm. Next, ripple factor zeta is equals to under root Vrms by Vdc whole square minus 1, that is that is equals to under root Vm by root 2 by 2 Vm by pi whole square minus 1, that is equals to pi by 2 root 2 whole square minus 1. You will get 0.482. okay, then ripple factor will be 48.2 percentage. When compared to half wave rectifier, this value will be very less. Okay, that means the drawback of the half wave rectifier will be overcome here. Next, efficiency neta is equals to output power by input power, right? Output power is nothing but IDC square into RL. Input power or AC per input is equals to IRMS square into RF plus RL. Okay, that is efficiency neta is equals to IDC square into RL by IRMS square into RF plus RL. Okay, that is equals to IDC value will be 2 Im by pi whole square into RL. If I take here RL as common, I will get Im by root 2 whole square into RL, bracket open, 1 plus RF by RL. This value will be very less. I can neglect that value. Here Im square and Im square will be cancelled, right? 1 by root 2 whole square will be 2. Here already 2 square, that is in numerator. This 2 will goes to numerator, that will get 8 by pi square. That value will be 0.812. Then percentage efficiency will be 81.2. In case of half wave rectifier, efficiency is only 40.6%. That drawback also overcome here. Next, transformer utilization factor. See here, in this case, input power is nothing but again Vrms into Irms, right? Here also Irms value here already same, we are getting Vm by root 2, right? Then if you simplify this equation, you will get same as like this only. You will get 81.2%. Transformer utilization factor also improved, right? That means the drawbacks in half wave rectifier will be overcome here. But the major drawback, this center tapped rectifier will be peak inverse voltage is high, that is minus 2 Vm, and another drawback will be the cost of the center tapped transformer is high. Okay, to avoid those two drawbacks, bridge rectifier is introduced. Okay, bridge rectifier will discuss in next class. Thank you all.